In this demonstration, we're going to show how you can convert to Simscape-based SimDriveline. Our model consists of a vehicle powertrain built using the original SimDriveline library. The components in this model are ideal, and we would like to add additional effects into our model, including friction losses. To do that, we're going to convert to the Simscape-based SimDriveline library. We'll do that in 3 steps. First, we'll run the command sdl-update, which will convert the model, all components and subsystems, to use the new Simscape-based library. Next, we'll change to a recommended solver, ODE15S or ODE23T. Finally, we're going to break or eliminate algebraic loops in our model. I'll now switch over to the model so that you can see how this is done. Here is our vehicle powertrain model. It has been built using the original SimDriveline library and contains ideal gear models, tire model, longitudinal vehicle dynamics model, and we can see in the transmission a number of clutches and planetary gears. We'd like to convert this entire model, preserving the structure, but using the new Simscape-based library. The first thing that we'll need to do is run the command sdl-update to convert this model to use the new Simscape-based library. The converter has run, and we can see that we have a new model with labeled _new, and if we go back into the subsystems, we can see that we are now using the new Simscape-based library. The connections have changed slightly. The next thing we'll need to do is to use a recommended solver. We'll go to Configuration Parameters, to the Solver pane, and change the solver to ODE23, one of the recommended solvers. The last thing we'll need to do is to eliminate or break algebraic loops. To see which algebraic loops our model has, we'll go to Configuration Panel, Diagnostics, and set the diagnostic for algebraic loops to Error. When we update diagram, we'll see any algebraic loops that are in the model. So I'll press Ctrl-D to update diagram, and we can see that in this error highlighted in the model in red. The loops in this model are between the engine and the engine controller, and if we go into the engine subsystem, we can see that there are 3 signals that are affected. The speed of the engine, which is sent to the controller, is affected. The oxygen signal that is sensed and sent to the controller is affected, and we can see a feedback loop where the speed is sent to a thermal model, which is a model of a physical system. For these 2 signals, which are sent to a discrete controller, we'll break those with a unit delay. For this signal, which is fed to a continuous model of the thermodynamics of the engine, we're going to use a continuous filter or a lag filter. To see what sample time we should use for our unit delay, we'll go to Sample Time Display and set it to Colors. We can now see which different sample times are in our model. The controller is highlighted in red and uses a sample time of 0.01. So we'll use that in our unit delay. We'll go to the Simulink library browser, and in the discrete library we'll bring a unit delay into our model and put it on the signals that are fed to the controller, setting the sample time to be 0.01. We'll copy that to this other signal sent to the controller. For the signal fed back to the thermal model of the engine, we're going to use a lag filter. We'll go to Continuous, get a transfer function, put it on the line, and set the time constant to be faster than we expect the speed of the engine to change. At this point, we believe we have broken all algebraic loops. We'll update the diagram again to see if we get any error messages, and we see that we do not. So at this point, we can now run the model. With these 3 steps, using sdl-update to translate the model, selecting a recommended solver, and breaking the algebraic loops, we have converted this model to use the new Simscape-based SimDriveline library.